A kite caught in the wind is kept at a fixed height of 60 meters while the wind is blowing the kite away from the person holding the string at a horizontal speed of 5 meters per second. At the instant the length of the string is 100 meters, find the rate at which the A, string is being spooled out, and B, angle above the horizontal the string makes as the ground changes. So we have a triangle here. Since the string is much longer than the height of the kite, it must be at a diagonal. So the kite is up here. It's being kept at a fixed height, so the height side of the triangle will remain a constant 60 meters, and we can label the 60 meters on the picture. The length of the string is not constant, it's being spooled out here, so we don't want to label it as the 100 meters on the picture. We will label it as a variable on the picture. It will be changing. And if that's changing, so is the horizontal leg of the triangle. Let's label that as X, and we'll label this as Z. What we're given here is the kite is being blown away from the person with a horizontal speed, which is telling us how much this horizontal distance is changing. So that 5 meters per second is the rate with which x is changing. It will be the x prime or dx dt, simply because x is measuring the horizontal distance to the kite. And it's being blown away, so therefore it'll be a positive 5 meters per second. We're also given that the length of the string will be, at this instant in time we're looking, 100 meters. So z will be 100 meters at this instant, though it will be changing because string is being spooled out and it will continue to become larger. For part A, we want to find the rate at which the string is being spooled out. That will be the rate of change of the length of the string, which is the hypotenuse z. We want to find z prime. We have x prime. We want to find z prime. We need to relate z to x. Well, z and x are sides of the right triangle. The z is the hypotenuse and x is one of the legs. They're related by the Pythagorean theorem. One leg squared, x squared, plus the other leg squared, 60 squared, equals the hypotenuse squared, z squared. There's the related variables equation. We can take the time derivative of both sides of this to come up with the related rates equation. I will indicate the time derivative of both sides by a prime on both sides. Every variable is implicit with time, so when we take the derivative of every variable, we will get a prime on every variable. On the left side, the first term is the power rule. Bring down the power, subtract 1 from it, and then multiply by the derivative of the inside. That will give us a x prime due to the chain rule. The derivative of 60 squared is 0, since 60 squared is a constant. Equals to, on the right side, we have a power rule. Bring down the power, subtract 1 from it, and then multiply by the derivative of the inside to complete the chain rule. That'll give us a z prime. Every variable is implicit with time, so we should always have a prime of the variable for every derivative. We can divide both sides by 2. The 2's will cancel. Here we want to solve for the rate at which the string is being spooled out, z prime. We need an x prime, and a z. We have an x prime and a z. We do not have an x just yet. However, we have a relation of variables between x and z, so if we know one, we can find the other. So we'll plug the z value into that equation. I'll work that out down here by the picture. So x squared plus 60 squared is equal to z squared, Pythagorean theorem on the triangle. X squared plus 60 squared equals 100 squared. X squared plus 60 squared, 6 times 6 is 36, and the square of the 0 makes 2 zeros. On the right side, 1 squared, 1 times 1 is 1, and the square of the 2 zeros makes 4 zeros. So that comes out to 10,000. We can subtract 3,600 from both sides. That will give us 6,400. And we can now solve for x by taking the square root of both sides. The square root of 64 is an 8, and the square root of 2 zeros makes 1 0. Now when you take the square root, you technically get plus or minus, but x is a measurement here, so we will only keep the positive. X is a length, and therefore to have units of the length in this problem is meters, 80 meters. That can now plug in for x in the related rates equation in part A. So we have x is an 80, x prime was given as a 5, z was given as a 100, and then z prime is what we are trying to solve for. 80 times 5 is 400 equals to 100 z prime. So we can solve for z prime by dividing both sides by 100. That gives us z prime is equal to 4. So z prime, or dz dt, is equal to a positive 4, and we'll have units of z, which is a length in meters, over time, which is seconds in this problem. By being positive, that means string is being spooled out. For part B, we want to find the rate at which the angle above the horizontal the string makes with the ground changes. So we want to look at how the angle of the string to the ground, let's label that on our picture as theta. That'll be there. We want to find the rate with which that changes. Theta prime, that'll be called. To find theta prime, you need to relate theta to one of the rates that we know. We're given x prime and we just found z prime, so we could relate it to either of those. It works out either way. If we relate it to the hypotenuse z, we can make use of maybe the sine of theta. One thing we will want to use is the constant side of the triangle, so we will want to use the 60. And sine of theta will equal the opposite side of the triangle, which is 60, over the hypotenuse of the triangle, which is a z. That's a related variables equation. We can then find the related rates equation by taking the time derivative of both sides. Before we take the time derivative, we will want to rewrite the right side so that we don't have to use the quotient rule because the numerator is actually a constant. Bring the denominator up as a negative first power. So we have the time derivative of each of these sides. On the left side, we have the derivative of sine of theta, which is cosine of theta, leave the inside alone, and then multiply by the derivative of the inside, theta prime, equals to, this will be a power rule. Bring down the power, negative 1 times the 60 will be a negative 60, z to the subtract 1 from the power, negative 2, and then multiply by the derivative of the inside of the power. The derivative of the z will be z prime. Every variable here is implicit on time, and we'll have a prime every time we take the derivative of it. We will want to rewrite that right side. So cosine of theta, theta prime equals to negative 60 will stay in the numerator. Z prime will stay in the numerator, but that z to the negative 2 will move to the denominator as z to the positive 2. We can now plug our numbers in. Cosine of theta is equal to the adjacent side, which is the length of x, that's an 80, over the hypotenuse, the z, and that's a 100. Cosine of theta is 80 over 100 times theta prime equals negative 60 times z prime, which we found in part A to be a 4, and then all of this over z squared. Well, z is 100, so 100 squared. Now, instead of getting really big numbers, we can reduce some of the numbers on each side. The 100 in the denominator on the left, and one of the 100s in the denominator on the right can cancel with each other as long as they're in the same position. Multiply both sides by 100. Those will cancel out. So I can now divide both sides by 80, and theta prime will be negative 60 times 4, which is negative 240. And then I'm going to be dividing both sides by 80, so there will be an 80 in the denominator as well as the 100 that is still there, since only one of them canceled. Now, instead of multiplying the 80 by the 100 and reducing from there, we can divide the 80 into the 240, and that will give us a negative 3 over 100. 240 divided by 80 is 3. This cannot reduce any further, so there's our result for theta prime, or d theta dt. It's a negative 3 over 100, units of theta angle, radians, in over units of time, in this problem, seconds, radians per second.